This is Jim Hendershot again. This next lecture number 12, is actually a supplemental lecture to the last one. It also covers stator laminations and stator cores, but we go into more details on this lecture on some of the issues with respect to how you actually design the laminations and the core. So let's begin with a picture, a cross-section picture of each of the three machines that we're discussing in this lecture series, and even though each picture here shows a different stator lam, they're essentially all very similar. And let's start with the induction. And as I have indicated in other lectures, we want to assume some sort of air gap circumference flux density as high as 1 Tesla. I doubt if we can get it as high, but let's shoot for 0.8, 0.9, 1 Tesla. And all the stator teeth then, because they're connected to the air gap, all the stator teeth have to carry that total flux. So if you have 4 poles, why each pole is represented by so many teeth, so that all those teeth have to carry the flux. Now, for low pole numbers, the maximum open circuit tooth flux in a brushless motor would be 1.7 Tesla. Of course, we don't exactly have open circuit situation with flux. In an induction motor, if you have open circuit, why there's no flux in the machine at all. But a high pole, if you have a high pole number in a PM machine, your open circuit tooth density would be in the neighborhood of 1.4. For the yoke, the flux density in the yoke for all these machines is based upon 50% of the pole flux, because the pole flux splits when it goes through a set of teeth. It splits and goes, half of it goes clockwise around the stator, and the other half goes clockwise around the stator. It's not going to go around one side and not the other. So the total lines of flux, or the flux, is less, but the flux density is split in the two sides. And since the mass of the stator yoke is usually higher than the mass of the teeth, one would allow the tooth flux to be a bit higher than the yoke flux. Now, a reluctant synchronous machine, let's assume that we desire the same flux density from the in the gap as the induction motor, but the stator teeth only carry 2/3 of the total air gap flux. They don't carry all of it. The flux density in the teeth and the yoke's about the same as an induction motor. For a permanent magnet machine, the flux is determined by the flux per pole from the permanent magnet. So there is an open circuit tooth flux density there. And the teeth that span actual magnet pole carry that rotor flux. So some of the teeth in between the poles don't carry any rotor flux at all when on open circuit. So the same flux density guidelines, I think, the bottom line here, can be used. Now, what the stator pole slot combinations for three-phase balanced windings? We discussed that in the last section, and I gave you a chart of the ones to avoid. This time I'm going to give you a chart of the ones that work. So that here we have a chart of, we have slots on the vertical, and that has to be divisible by 3 if it's 3-phase. Has to be divisible by 4 if it's 4-phase, or 2 if it's 2-phase, but 3 for the 3-phase. And across the top we have the number of poles. And of course, since poles have to be in pole pairs, the number of poles has to be divisible by 2. So every place you have an X, you have a possibility for a balanced winding. A 2-pole machine will work with every possible number of slots. But one of the most difficult ones is a 6-pole motor has a minimum number of slot combinations that will give you a balanced windings. And then, of course, multiples of 6, the 12 and 18 and the 24, they all have the same difficulty of having enough options. And the reason that other combinations don't work is because you can't get identical sets of phase winding distributed around the stator 120 electrical degrees apart. That's why you don't have X's in some of those other combinations. It's basic number theory. It just doesn't work out. But when you punch, as we said before, you punch a rotor lamb out of a stator lamb, and this example on the right shows a bigger air gap than it's realistic. But we have you have the choice of a round slot bottom or a rectangular slot bottom. Now the rectangular slot bottom gives you a little more winding space, and it's quite easy to form your slot liners such that they, with a rectangular slot, it's easier to form the slot liners. There's a lot of argument about whether you should use round or rectangular. I would say that it's probably, I'm not sure if it makes that much difference other than the automatic insertion equipment that are used in the induction motor industry. The tooling favors the round slot bottom, and I'm not sure why, but it does. It seems that if you make the tooling fit these rectangular slots, you have more difficulty getting the automatic insertion of the groups of coils that have been pre-wound, that are dropped down in the slot. So, but then you have the slot openings magnetically. You want to keep the slot opening as small as possible, both the rotor and stator. But for ease of manufacturing, you want them as wide as possible. So that's a trade-off that has to be dealt with. There should always be radiuses in the corners of these teeth. They shouldn't be even as sharp as that's shown. Because you'll get flux concentrations around there, high flux densities around the corners. And the sides of the teeth should have tapers on them. There can be a radius right there. That's okay for a radius there. But the sides of the teeth should have taper. The distance of the length of the tooth, tooth tip that extends past the side of the tooth. In other words, the distance from here to here should equal that distance there to avoid saturation. So the tooth tip extrusion should protrusion should be equal to the throat thickness or the attachment of the tooth tip to the tooth. The yoke thickness of the stator is based on the requirement of the number of poles. So with a given size rotor, you have twice as much flux per pole as you have with a 4-pole motor, or 4 times as much flux as you have with an 8-pole motor. So if you have twice as much flux, or look at it the other way, you have 1/4 as much flux, then the yoke thickness only has to be 1/4 of as thick. So you can use that extra space a couple different ways. We talked about that in the last lecture. And now here's some flux. I gave you flux density guidelines before, on the first slide. But here's some flux density guidelines that maybe are more important than my suggestions. But these are based on the advice given by 2 experts, Tom Lippo, a famous professor from the University of Wisconsin, and a very famous motor engineer from years gone by the name of Say. And Say recommended in induction machines an average air gap flux density of 0.65 to 0.82 Tesla. And Lippo didn't provide that in the same reference that I found these flux densities, but I think it's safe to assume that he was using the same kind of numbers. So Lippo was more. There's one distinct difference between these two guys that I think is interesting, and that is that Say never designed any induction motors for inverter duty, because you didn't have inverters in those days. All his work was done with fixed voltage and frequency, 50 or 60 hertz machines. And Lippo, most of his work was done with induction motors that had to be inverter driven, because that's more modern, and University of Wisconsin is very famous for flux vector control of induction motors. So he allows higher flux densities across the board because he can control the magnetizing current, and he can control the torque of the machine better with an inverter duty. So he wants to get higher torque density out of the machine, so he runs the flux densities higher. But you just have to deal with the losses. Now the open circuit flux densities for PM machines are a little lower than induction because you have to allow for when the flux density goes higher when you apply current to the stator. Now the air gap between the rotor and the stator, if you remember, let's go back to this picture right here where you show the where we show the air gap and we show all these slot openings. Well, it's one thing to just take this air gap and say the air gap is 25 thousandths or 10 thousandths of an inch or half a millimeter or 1 millimeter. But in calculating the motor to determine the ampere turns required to drive flux across that gap, you have to deal with the slot openings and what's used to compensate to make the effective air gap seem larger is you use these Carter coefficients for estimating what the effect of the slot openings is to the total air gap. So some people use this and some don't. It's not as often used in PM machines as it is induction because the air gap is so critical in an induction machine, and the regular air gap is so small and the slot openings are so big that the Carter coefficients are so important. But in a PM machine, the air gap is quite large, and the slot openings tend not to be as large in a brushless machine. So it's less important with PM machines than it is with reluctant synchronous or induction. Now here's some examples of some different punchings of stator and rotor lambs. You see these up here are this is a rotor for induction motor rotor. This is an IPM motor made by A.O. Smith. This is courtesy of an engineer from A.O. Smith who now works for Vestas. And this is an IPM also, but here you have a slab magnet that goes that way with almost no reluctance component of torque. There's no soft salient pole in between the magnets. And this example here, they wanted to put this soft iron in between the magnets to give this thing saliency, to get a reluctance torque component. So to get the same magnet area, you make the magnet in two pieces and put it in a V, and so that's what that makes that look like. This is an interesting way to make a stator. This is a slinky method. It's a very clever method to make a stator because a fairly thin cross-section yoke and tooth, and if you punch that out of a round, a completely round or a square piece of steel, you'd have a lot of waste. You'd waste the corners and the ID unless you could punch the rotor punching out of it. So that's a very great way to make stators. It's been used for many years, originally patented by GE, but in Fort Wayne, but the patents have all run out, and now this is made all over the world. This is a standard progressive die used to make these rotor, this sort of rotor stator punching set is made in this type of a progressive die with each station taking out some of the portions of the stamping. Here's a couple of pictures. Here's 2007 Camry stator and a 2008 Toyota Lexus stator. These come from the work at Oak Ridge Labs. They provided these for me, and as you can see, what's interesting is these all have round bottoms. They're permanent magnet IPM machines. They have round bottom teeth or round bottom slots, and the slots are tapered, and also on this one the teeth actually have a slight taper to them. Maybe both of them do. I'm not sure. But I think what's interesting about this is they have added places for welding this core on the OD. I don't think that's necessary, but they've added it there. They would TIG or laser weld that and melt this little protrusion together there. And I guess they got enough yoke thickness they could do it, but notice they put it over the center of it too. The other thing I find it's interesting about these punchings is that for mounting this thing to wherever it mounts to, they've added these little ears here with holes in them to mount. And that's a heck of a waste of material to do that. I'm surprised they do that. It seems to me if they use 4 of these instead of 3 and put them on the 4 corners, you would use less material. See, to punch this, if you draw a square, a square like that, you have all that waste. Whereas if you put these at 4 of these, then you wouldn't have as much waste. You'd have a smaller. The square would fit within a square of the OD rather than the square of the outside of the protrusions and the OD. So I find that noteworthy. Here's a picture of a whole bunch of cores that have been stacked different ways. Some are welded, some are bonded, and some are insulated in different ways. This is a case where you make an insulated end board to insulate the end of the core. You see one mounted here. And these colored ones, these are cores that are insulated with an epoxy coating material, which is a 3M product. That's a very good way to insulate a core. The application process puts a uniform coat on the ends and down the slots, and no insulation on the OD where it's got to fit in a housing, or on the ID where it's got to maintain an air gap. And here's another picture of how the cores are made. This is a cleated core. There's a notch punch in the OD, and then this steel. They're stacked on tooling and arbors, and then this cleat is forced in there and kind of flattened with wedges itself and holds the thing together. This example is, and this shows the effect of eddy currents and why they're laminated, but here's a strap over the OD that clamps it. It's like a big clamp over the OD in several places. That's not used much anymore. But here's some examples of welded. This is a very poor welded core that has filler metal added. It takes up. It's way too big. It's going to cause eddy currents in there. It's a poor weld. Here's very excellent weld. Very tiny, small welds. That's desirable. And this is the die interlock core. And this is very interesting to see. You punch these little detents or louvers or grooves or interlocking grooves into each lamb, and as the lambs come out of the die, out of the bottom of the die, a plate forces them together, so they nest together, so you wind up with a stack. And they even are able to skew these stacks. In other words, they have servos that will rotate the notching station, or the dimpling station, so that when it puts these together, it gives you a natural skewed stack. Now, I think it's important to note here what a bad job this is. You see, that skew is not uniform. See all this jaggedness? Well, that cuts into the slot opening. If this is an induction motor, then you've reduced the cross-section of the die-cast aluminum material. That's a very bad job of, that die needs maintenance. The servo system that does the rotating of that interlocking notch needs attention. It's a very poor job. I'm happy to have this picture to illustrate that to you. This is a picture of a core that I showed on the last one, a close-up view. This one is stacked and bonded. Now I'm going to show you some pictures of a finger plate on the end of a stack, and this is a case where, in retrospect, I should have used a finger plate on this, because these teeth are very long. And yeah, they're bonded, but as it turned out, not all of them, the bonding didn't take on all the teeth on the ends, and some of these actually stuck up a bit. And so I should have put a finger plate, a heavy piece of steel that goes on the OD here, and has things that look like the lamination, but they're not. They'll be narrower, and they'll be pre-bent downwards. You know, from this point they'll be bent down. So when you clamp it on the OD, those act like finger springs that compress all these together. I'm going to show you a picture of it later. I should have had those on a machine this big. Now this is an example of a core that is made by making T-shaped segments of the yoke. You see, each one of these is a sintered tooth and yoke. I showed you a picture in the last one of that. And then you use bobbins and layer wound coils that wind up with very high slot fill, and it's a very low cost way of making the machine. This shows you, this is a beautiful picture that shows this die interlocking principle that I from this picture here, and this is a cross section of what those interlocking dimples look like. And so here's an excellent stacking job of the proper servo rotating of this interlocking dimple. See, that's a very uniform skew on that. Here's one that's skewed very clever. You can get a thrust force from this skew. Now here's an example of a rotor that's going to be die cast, so it didn't matter. They skewed half of it and then they went back the other way. So there's any axial forces cancel each other on this, but you still have the effects of a skew, which is beneficial for an induction motor. Now here's an example of these finger plates I was talking about. They use this in large cores, and you see there's your stack of lambs, and this is a finger plate. This is a heavy steel plate that pushes down on the ends of the teeth. It pushes down on the teeth at the ends of the core. They have one of those on each end. Now this is a very interesting picture also. Those same finger plates can have pieces of steel welded to them, and that's used for end turn support. Remember, in a previous lecture I showed you some pictures of end turn supports. Well, this is an example of how to do that. And by the way, these are cooling passages in this core. This is a big core for maybe a wind turbine, maybe some big generator. Not sure what it's for, but these are welded bars that stick out from this finger plate that are used to lace the end turns to for support. Now, and here's that other picture that shows the finger plates, and you could, it's a different one, but it's a different version of the same idea. But even this finger plate assembly could have end turn supports on it. But now here's an example of vent plates. This is not a vent plate, or this is not a finger plate. That's a vent plate, and the vent plate are made of a heavy piece of lamination with some little pieces on it used for support. They're spot welded on there, and you see these are little spot welded little bars that come up that when you put the next group of lambs on top of this, that provides a space. But then you have these vent passages through here, and vent passages through here for the cooling air or gas to go to cool the cores. That's what and you see this is a plate with little bars spot welded to it, and that's what provides the gap of the space between in the core. We talked about sintered magnetic cores in the last one, and here's some examples of Höganäs, I'm not sure how you pronounce this, from Sweden. They're a well-known supplier of powdered materials, and they have a whole product line of pure Swedish iron, pure iron with no carbon in it. They have a product line of of Swedish iron with silicon in it and phosphorus and various things like that to minimize core loss. And then you can buy that material and you could sinter it, you can coat it with epoxy and bond the cores together, things like that. You make very complicated shapes. It's popular in some. These are both axial flux motors. You see those little pole pieces there? This is a radial flux. This one's axial flux, but I showed you this in a previous slide over here. Yeah, this one right here. These pole pieces are sintered, and this is a shorter version of it. So if you have this part, you insulate it, either powder coat it or put a molded plastic part around it, and then you wind right on it. You layer wind such that you have a very high slot fill, not much wasted air, and then you put them all together and bond them together or shrink them in a tube or whatever. You can get complicated 3D shapes out of this that you can't get out of laminations. Here's some other ways to make cores. This is that slinky method. You see an example of how the slinky method is made. And for axial flux machines, you can make some pretty weird parts like this. This is pretty clever. You could build an automatic machine to fold this like ribbon candy and make a axial. See, the flux goes through this thing like this. You got a rotor on each end, and this is your stator. So your coils are wrapped around this thing this way. Okay. And this is a IPM, an internal magnet brushless motor where the rotor punching is punched out of the hole of the stator. That's a very good example. And this is another technology that's similar to the slinky, and this is widely used. Honda uses this. A number of companies use versions and variations of this, and they all have patents. Sometimes this is done with a single tooth, and other time it's done with multiple teeth. So if you have these multiple teeth here, you can do a couple of things. If with multiple teeth, you only do this with these hinges built in it to build a core with very low iron losses. That's really the only purpose of doing this. If you play a trick like this with hinges and you have an individual tooth, then you can wind on them while you're in the linear state and then wrap it up later. And there are people who do that. So that's the end of this lecture. Thank you very much.